Thank you, everyone. Thank you for joining us for Power Electronics Talks. So today we have Kaibalya Prasad Panda. He is a Ph.D. research scholar at National Institute of Technology, Meghalaya. So today he'll be giving a talk on advanced multi-level inverter for renewable energy systems. Thank you very much, Kaibalya. Please go ahead.
Thank you, sir. So, hello everyone. A very warm welcome to this Power Electronic Talk, and I shall thank Dr. Janmajaya for the invitation to this platform. And it's a great pleasure to present my work to you all. So today's topic of this presentation, as you can see on your screen, this is advanced multi-level inverter for renewable energy systems. And to give a brief about myself, I am a PhD research scholar, and myself, Kaibalya Prasad Panda, in the National Institute of Technology, Meghalaya, Shillong. So I am working under Professor Gayadhar Panda, and around like 3.5 years, I'm working on this field. So uh, quickly, I'll go through the outlines of this presentations. So I'll be covering here about the multi-level inverter and how this advancement on multi-level inverters has been done. That is, what are the different reduced switch types and reduced component-based inverter types. So that I'll be discussing here. Then I'll go through one of the implemented topology here, what we have implemented in integration with photovoltaic system. So, and what are the different issues with that? So that I'll be discussing again. Then I'll present the paper, two of my papers, what got recently accepted related to switched capacitor type. So what is this switched capacitor? How it has got evolution, and how it is now playing a important role in designing any of the multi-level inverters. So I'll be discussing related to that. And also I'll go through what kind of different aspects we need to consider for designing a multi-level inverter topology. I'll also discuss that. Then we'll see some of the important results in simulation and experimentally. So as I have told, this multi-level inverter, so what is it actually, and where from this term came? If we see any of the photovoltaic system, like renewable energy systems basically, and this growth in renewable energy systems in the current world, if you see, that is due to the advancement in the power electronic sides only. So I think there are many other researchers, they have also given talk on this power electronics. So they might have introduced regarding this different types of switches and power electronic converters, what got recently developed, and that is playing a big role in advancement of the photovoltaic system. Basically, I'm focusing on photovoltaic system. You can consider any of the renewable energy systems. And here in this type of systems, the inverter is the heart of these systems, we say. So what this inverter does, it converts basically from the DC to AC. And while this DC to AC power conversion, if we want to improve the power quality, or you can say voltage quality, everything, this power quality improvement can be achieved in a majorly it can be improved by using multi-level inverters. So we can replace this conventional inverters by multi-level inverter. As the name suggests, multi-level, as the name suggests, the output of voltage will be generally of the different voltage steps. So as there are many number of steps in the output voltage level, so obviously the harmonics on the voltage will be reduced. So because of that less harmonics, obviously power quality improvement we can achieve. So that is the idea of multi-level inverters. And what is the problem with this is, when we see different conventional multi-level inverters, that I'll be discussing a bit of it. So if you see conventional multi-level inverters, that requires a large number of like switches, components, other components like passive components, you can say, the capacitors, diodes, and all these things. And when capacitor, diodes, that came into picture, then obviously balancing is the again a problem, voltage balancing. And the components that will incur more cost, and also that will cause the size to be increased largely. So that is the problem with this conventional inverters. So that is why still the research is going on in the field of designing a compact module or reduced switch type, what I call. So reduced switch multi-level inverters design. So that is the recent research focus, we can say. And with respect to this reduction in the switch, we can see what I will here also present. There are a lot of development now towards reducing the number of sources, because in terms of photovoltaic application or any other applications, if we see, if there are number of sources as there, that will again cause difficulty in controlling the system. So that is the major problem. And also in terms of cost, size, and everything, we can optimize the inverter design by using this switched capacitor concept. So that is the concept here. I'll introduce what is switched capacitor inverter concept and how it is now optimizing and playing a major role in designing this new multi-level inverters. And with again with introduction of this switched capacitor type multi-level inverters, I will also introduce highlight here that because switched capacitor, when I say there are involvement of large number of capacitors, definitely. So if there are some capacitors are there, then we need to focus on how to balance the voltage across it, because the inverter, there are also inverters designed using this switched capacitor concept, but there is no voltage balancing ability, like self balancing, what I call self balancing here. If we can balance the capacitor voltages inherently without using additional control logic or control complexity or auxiliary control circuits, I can say, or also sensors, what I call in terms of experimental or real time work, if we see, if we don't need any sensors or auxiliary control circuit to balance the voltage across the capacitor. So that is one of the advantage, we can say, that is one of the biggest advantage of this switched capacitor type topologies. So that type of design and application will also be in the photovoltaic system, and also power quality of different systems, like if we see traction drives, electric vehicles, statcom applications, and photovoltaic system, I have already told. And in different applications like this switched capacitor topologies are also now gaining importance, but multi-level inverters have already replaced this three level inverters in all these applications. So in one of the major application is in terms of in the field of high frequency AC power distribution systems, because the switched capacitor type is there, so capacitors are involved. So if we operate the inverter in high frequency, obviously the capacitor ripples will be reduced. So that is one of the advantage. And due to that, this switched capacitor multi-level inverters have also used in the high frequency AC power distribution systems. So these, with these applications, we can see there are three different conventional this multi-level inverters are developed with three different logics. One is the neutral point clamp type, what I have just highlighted here, NPC. And second one is the flying capacitor type. As you can see, there are a number of capacitors involved here. And the third one is the H-bridge type. And if we, these are all three level types. And if we want to increase the level, because these are three levels, and multi-level and what we call, we start from like 5 level, 7 level, like that. If we want to increase the number of levels, now we can think here the number of diodes in the first topology, neutral point clamped, there will be number of diodes increased. And because of this series connection of this switches and these diodes here, there is a high chance of module failure. So that is a problem here. And if we want to increase the number of levels here to produce high number of levels, you can think of how many additional number of diodes are required. So that again causes a problem with respect to size, cost, and volume. Similarly, in the flying capacitor type, if we because there are number of capacitors are there, flying capacitors, so voltage balancing is the major issue. I told whenever there is a capacitor in the circuit, so voltage balancing is one of the key designing or designing aspect, we can say. So this capacitor voltage balancing is one of the major issue in flying capacitor topologies. So this with respect to all this, if we see, no doubt this all these topologies like neutral point clamped based systems and flying capacitor based topologies, they have also used in the photovoltaic systems. But with respect to this scalability and modularity, if we see the cascaded H bridge type, what I call CHB type, that is highly modular, No doubt that also requires number of switches, but still it is highly modular and controlling will be easier. And we do not need additional passive components like diodes and capacitors here. So that is again an advantage. But as you can see here, what I call cascaded H-bridge type, you just think of this H-bridge module here. If I connect in cascade fashion another H-bridge, so that will create 5 level, because this topology what is here, uh, just a second. So this circuit here, if we see the voltage output of this the 3 level, so that will be something like this, like in positive level and negative level. So because of this VDC input, this will create VDC here, and there is a 0 level. Obviously, 0 level is there. That is by switching on of this upper two switches or lower two switches, we can create a 0 level. And this is minus VDC. So as you can see here, there are 3 levels like VDC, 0, and minus VDC. So that is why this circuit, as we know, this is single phase circuit, and this circuit produces 3 level output. But now if we think of cascading it, that will create a multi-level output. So multiple steps will be there. So now you think, if I just cascade this same inverter of 4 switches with another 4 switches inverter, so if I connected in cascade fashion, obviously there will be 5 levels, because this input VDC, if I am taking this input VDC equal for both the inverters or both the circuits, both the modules, you can say. So then there will be first step will be VDC, there will be second step 2 VDC. So the output will be something like this. There will be VDC and 2 VDC. So this is the 0 level, we can say. Okay. So here we are producing 2 steps. But another important aspect here I want to highlight here is that not only here, why it is mostly used. So not only your symmetrical case, what I said here, VDC and VDC two sources, if I take, that is the case of symmetrical. But if I take VDC here and another source, what I connected in cascade fashion, if I consider that is 2 VDC, so in that case, I can also produce VDC here, 2 VDC there. So that is in 1:2 ratio you can consider. If you are considering like that, that type of system is called asymmetrical. So asymmetrical topologies create higher number of levels. But with that, again, we have also to consider, because we are considering more voltage there, 2 VDC and here VDC. So that will also increase the stress across the switches. So that is again another important point to highlight here while designing. That is the voltage stress across the switches. So like this, the inverter works. And here,
Just one question, Kaibalya. Can you
yes,
just
yes.
highlight what is the chief motivation for going to more levels so that the audience understands why
Yeah, yeah, yeah.
people are going for more levels?
Sure, sure, sure. I'll just highlight after this, sir, that
Okay,
point.
okay, okay,
Yeah. I may after this, if anyone is getting the doubt, then I'll definitely clear it.
okay, 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 okay.
Sure. So here, these are different real-time inverters in the industrial level. What is implemented, the neutral point clamp, cascade HV type, this ASI, Rubicon, Siemens, Alstom, they have installed this different inverters. So what I want to highlight here is that multi-level inverters have also replaced the 3-level inverters in the industrial level. And one of the last one is, this is the one of the current source type, Rockwell, who implemented. So there are other companies or industrials, they have also used this inverters for different applications like drives application, and another one I've seen that is used for statcom application. So like this. So different applications, multi-level inverters have successfully replaced. So what I told here up to this, so accordingly, if we see this reduced switch multi-level inverter types, so that I basically divide into a single source or a multi-source. Here, just going back to the previous slide, if we see here, this circuit, this is no doubt a H-bridge module. What I show here, the H-bridge module, that is your this requires one single source. But we now, what I said, if I just want to cascade it, it is creating a multiple levels at the output voltage. So because of that multiple levels, if we go on increasing the number of levels, definitely the voltage quality will be improved, because it is nearing to the sinusoidal waveform. So that I'll highlight after this. So that requires multiple sources. So if you think of multiple sources, so that is a category here. I've made it multiple source type. Another category is single source. And whenever there is a multiple source, we can operate in symmetrical by maintaining the sources equal. Asymmetrical, that is by varying the sources in the different ratio, 1:2, or like that, what I introduced. Then another one, I have made a category of hybrid topologies. So all this, again, this multi-source or single source type, that are also researched in transformer based or transformer less applications. So in transformer less application, again, we need different aspects to consider, like the leakage current and common mode voltage. And in transformer based system, we can easily integrate this multi-level inverters. So these are the categories what I've made, and I'll show you some of the different circuits what is introduced earlier in the multi-level inverter field. Here, if you just see, these are all three different circuits I have taken here in the symmetrical case which are operating. No doubt these circuits can operate also in asymmetrical case. But here, this, if you see, there is a basic unit I have highlighted here in the first circuit, and this basic unit is repeated here, as you can see. So, and only one H bridge is used here, right? So this H bridge, what is the function of this bridge here? That is just creating the polarity, positive and negative polarity. And whereas this circuits here, basic units, what is shown, that is creating number of steps, right? So like this, different designs are shown here. So this actually is reducing the number of switches. Here, what I just highlighted in the cascaded H bridge type, if we just calculate what is the number of switch requirement with respect to number of levels, so that there is a basic formula. In symmetrical case, we can calculate using 2 times the nl minus 1. If number of level is nl, if I take, then 2 times nl minus 1. So that means if we consider 5 level, that requires 8 switches in the conventional cascade HVDC type. So in symmetrical case. And if we consider 7 level, that requires another 12. So if we go on cascading like that H bridge, so 4, 8, 12, like that, 4 switches will be going on increasing. But here you see this has reduced some of the number of switches, right? So because of this type of designs are called as reduced switch multi-level inverters. So there are various designs. Here, all these designs I have highlighted in one of our review paper, that is highlighted here, and you can refer to this paper. So here, this again, different topologies I have taken here, that is for the case of asymmetrical. Asymmetrical means obviously these sources are in a different ratio, that is not equal. Here, one of the important thing I just want to highlight, if we design an inverter like this to create multiple steps, what is happening with this? These 4 switches, the H bridge switch, that is T1, T2, T3, T4, these switches, they will face the maximum voltage stress, right? Whatever the voltage is there in the input side, that whole voltage will appear, the maximum peak voltage will appear across these 4 switches. So because of that, these high voltage rated switches are required here. And that again will cause the increase of total standing voltage. If I calculate what is the total voltage stress or total standing voltage, or sometimes called as blocking voltage also. So total standing voltage for this circuit, if I want to calculate, so that will be also high if I operate in asymmetrical, right? But anyway, the number of levels will be increased. So how this levels and that can be increased, that I'll just show you after this. Again, similarly, what I told hybrid case, hybrid is that if we just see the previous models here, there are H bridge circuits are there. H bridge means that is creating polarity. I told you this H bridge is for polarity changing. But here, if we see, you can clearly see that there are no such H bridges there to create the positive and negative polarity levels, right? So, but still it is producing the AC output, that is clean AC output this topologies can produce. So these are the some of the recent circuit developed. If we see here, these circuits can operate in symmetrical and asymmetrical also. And one more important thing is there is no H bridge. So why that H bridge is avoided here? That is the point what I highlighted, to reduce the blocking voltage or the voltage stress. So that is the advantage of these circuits. So like this also, there are different circuits are proposed, and focusing on this different types of symmetrical asymmetrical configurations, this is one of our proposed circuit. what we used in the photovoltaic system application, and it is connected to the grid connected system. So what I told you, what is this level? If you can see in the right hand side, there is a 15 level output. So how is this 15 level? If you see on the positive side, there are 1 2 3 4 5 6 7 steps in the positive, 7 steps in the negative, and there is a 0 level. So we are counting 15 level. This is a 15 level output. So this circuit has reduced the number of switches in comparison to the conventional circuit. That is one of the important thing here. The reduced switches are reduced, and we are achieving this output. If you see here, the multi-level output, how it looks like, it is looking like nearly sinusoidal output. So that is one of the advantage of increasing the number of levels. If I go on increasing the number of levels here, obviously the output will be nearly equal to sinusoidal. So that will, because of that, and we know output voltage of inverter is always square wave type. So if we increase the number of steps here, the output will be more nearer to sinusoidal. So that, because of that, the voltage quality will be definitely improved. And that is the main reason behind the current this many research work going on in the field of multi-level inverters. Because by reducing the number of switches, if we can produce the same output still, so that is one of the advantage. So that is why we need to focus on reducing the switches, reducing the sources, but still we want this kind of output, because to increase the voltage quality. So here in this system, if we see, there are what I want to highlight here, there are number of sources, number of PV panels I have used here, 1 cross 1, 2 cross 2. Why I have taken? Because to take asymmetrical voltage I have to maintain here. And if you see, there are number of PV panels, that will incur more complexity in the control scheme, because this requires a complex control scheme when designing and controlling in grid tied applications. And I have highlighted here, this requires individual MPPT control, because there are multiple PV panels. It requires decoupling voltage balancing, and also in grid connected system we need to maintain the harmonic distortion, harmonics to be reduced. So focusing in all this, then harmonics, when I say, that is one of the important point here. If I consider a 3 level or 5 level output, obviously the THD, the total harmonic distortion in the output voltage will be very high, right? So but here, as I've increased the number of levels to 15 levels, because the obviously the steps are or the output looks nearer to sinusoidal, the total harmonic distortion on the output voltage will be very less. And in that case, what will happen in practical grid tied system applications, the mainly the filter size, what we are connecting when you are feeding the output of this AC output to the grid or anything, so in that case the filter size can be reduced. So that is the main motivation here behind design or increasing the number of levels, so that filter size can be reduced, harmonics can be reduced, obviously in the output voltage. What generally in the 3 level or 5 level output, if you see, the total harmonic distortion may be nearly equal to 30%. Or here, if we see, in a 15 level output, the total harmonic distortion will be nearly maybe equal to 15%, halved. So that is how the harmonics is getting reduced. So obviously, if I want to use a filter here at the output side, so that filter size will be reduced. So that is one of the biggest advantage here. Low size of filters can be used for again making it sinusoidal or like that. So this,
Kaibalya,
yes,
just
yes,
one quick question. So,
yeah,
if I look at the switches, so some are stressed more than others, right? Like some are
yes, yes,
conducted.
correct, correct, correct.
So that you will take into consideration sometime, or that is not
No, no,
compared to
that is
reducing the.
yes, yes, that is one of the main key consideration here. Here,
Mhm,
if we see here, there are switches like these switches SN, S1, all these
mhm,
switches. These
mhm.
switches will face a low stress, whereas this
Okay.
T1, T2, T3, T4 switches, that will face
Mhm,
high voltage stress. So
mhm,
based on that, the design has to be or the voltage rating of the switches has to be designed accordingly,
okay. Okay.
because again that will cause otherwise more like design losses, and power losses also will increase.
Okay.
So
Okay.
we need to consider the voltage stress, that is a main design aspect. So I will
Okay.
also, so by the end of this presentation I'll also clear out how
Mhm.
to like optimize, how to optimize everything, every aspect of this design things.
Okay. Okay. Yeah. Please go ahead.
So
Please go ahead.
yes, yes, sir. So for this, what I highlighted here, this system, This control system, what I've just shown here for the 15 level output or inverter, photovoltaic based system inverter, the same control can be also integrated to with conventional cascade HVDC type, and also here for the reduced switch type I have just highlighted here. Why I'm telling about conventional HVDC type, because that also requires multiple number of DC sources. So multiple number of DC sources, in turn we can say multiple PV panels. So that also requires multiple MPPT control. So here we can see there are a number of MPPT controllers I have connected here. I have here used incremental conductance algorithm. That is not the focus of work, so I will not highlight much about incremental conductance. That is a basic conventional algorithm. And what is the important points to highlight is that number of MPPT controllers that is giving this. Then after that, what I've done here, I have used a total voltage controller module. What is this total voltage control module? Now that will maintain the total DC link voltage, because we have to anyhow maintain the DC link voltage for maintaining again the power quality and all. So total DC link voltage can be maintained by this loop, whereas individual voltage controller cannot be guaranteed if we maintain only the total voltage. So that is why again individual voltage controller modules also connected. That again helps in generating the reference signal for this PWM generation by the end. And after that I have used a current controller module. So what this is doing, this is maintaining the power balance for the maintaining the power balance. Current controller module is used, and PLIs is used for synchronization. And every these signals are then used for this. If we see on the down, there is a PD PWM control scheme or phase disposition PWM control scheme. So that is used here to generate the switching signals for the inverter. So that is how the controller works. And if I see so here the different results. So this is one of the experimental setup we have created for testing that inverter. And solar simulator is used here for in place of the photovoltaic panel. So here as you can see, first test is conducted with different modulation index. So this plays a major role, modulation index, because we know in terms of control, if modulation index is low here, we can see 0.5. So that levels are reduced here, right? So here I am producing around 1, 2, 3, 4, so 9 levels output. So if there is a 9 level, because we are expecting a 15 level output from this inverter, but this is producing now 9 level because of the references signal, and the modulation index is set to 0.5. But here, if I just increase the modulation index more than 1, you can see the upper level is more flatter. So because of that, again, the harmonics will be high, right? So we need to operate the multi-level inverter nearly at modulation index 1, where we are producing a clean 15 level output as desired. And also grid current, you can see that is sinusoidal maintained. So here inverter voltage THD and grid current THD I have taken from the power quality analyzers. That is also maintaining mostly this IEEE 5.9 standard, I can say. So by that inverter now, what is the conclusion from this is we need to operate at higher modulation index or nearly unity modulation index. So while maintaining this modulation index, another two tests are conducted here in the dynamic test case, we can say. Here I have shown the PV panel control layout here, the how the PV panels are set and all. And you can see that when there is a change in the insolation, sudden change in the insolation, and because of sudden change in insolation, we can see this grid current is majorly changing here. The grid current is majorly changing because of the change in insolation. Whereas other things are not affected, the 15 level output is still maintained, still produced because of the robust control scheme. And another dynamic test case result I have shown here, because during the sag condition or when there is a sudden dip in the grid voltage, simultaneously I have told here we have used a current control loop to balance the power. So that is acting here. Whenever there is a sudden change in the dip in the grid voltage, the grid current is increasing. Whereas again inverter output voltage is maintained as desired. And the red one here is the grid voltage, and the green one here is the grid current. So grid voltage, when there is a drop, grid current is increasing in proportionally. So that is to balance the power. So that is how the system works. And you can also see here this MPPT tracked. at different irradiation condition, if we see, the measured power and the calculated power are nearly equal, and the MPPT tracking is mostly more than 99%. So till this, whatever I have highlighted is the multiple PV panel control. When there is a multiple PV panels are there, obviously we need to control each PV panel. Like in the traditional system, 3-level output, we can see in the traditional system, what we use in the photovoltaic system generally, a DC-DC converter that is used for voltage boosting, because photovoltaic panels are generally available in low voltage rating. Then we use a traditional inverter. That inverter converts DC to AC, and we need to use for domestic and single phase grid systems. So these inverters are, when we use this type of inverter, which is producing a 3-level output, obviously the harmonics will be high, right? Now, because of that, we have moved to multi-level inverter case. So what that does, if we consider cascade H-bridge type configuration, let's suppose, or the previous configuration what I've shown till now, that all requires multiple PV panel. When there is multiple PV panel, obviously we need multiple DC-DC converters for voltage boosting. No doubt this can be avoided if we want to generally build a single stage PV system, but still multiple PV panels are required. So here, this multiple PV panel DC-DC converter control, again, it increases the control complexity, cost will be high, volume is high. But what you are achieving from this is this cascade H-bridge or any reduced switch topologies what I've introduced. This all creates multiple steps at the output. Like this output I've seen shown on the right hand side. This kind of output we are producing, no doubt. The voltage quality is improved. If we are achieving the multiple steps in the output, I told harmonics will be definitely reduced. So output, we are improving the output, but control complexity is more. So what is the idea here? What I proposed is using a photovoltaic system without using any DC-DC converters. Because if we can just boost, because DC-DC converter here we are using for boosting the voltage, and that voltage boosting, if we can do it in the inverter side, in the inverter itself, so that is the one of the advantage. So that is proposed here. The proposed systems inverter, if we see after this, this inverter will be used in, you can use in photovoltaic systems. It can be, it can achieve voltage boosting in single stage, and it doesn't require any additional DC-DC converters. So which again simplify the control scheme. So that is how this switched capacitor. So there switched capacitor inverter comes into picture when we need to avoid DC-DC converters. Also, we want to boost the voltage inherently, and so based on that, the switched capacitor inverters are designed. So before going into switched capacitor inverter, again here I have shown just to highlight, because to highlight the basics of multi-level inverter and how this switched capacitor inverter came into picture. Here you can see it or analyze it clearly. On the top, if you see, there is a 3-level inverter circuit. So there are 4 switches which is operating to get this output. See the output, that is 3-level output I said, plus B, minus B, and 0 level, right? And the lower circuit, if we see, now I have cascaded it, and I am just considering equal voltage sources, V equal voltage sources, but I have cascaded. What I just highlighted or discussed in the initially, here when I am cascading, you can see there are 2 modules cascaded. So it requires 8 switch, right? So 8 switches are now required to generate a 5-level output. You see the how the switches are operating, what is the switching pattern, that also I have taken here, right? So this is producing V to B in the positive and minus B to B in the negative cycle, and there is a 0 level, right? So you see there are 8 switches are required to generate a 5-level output. So there is a simple calculation also you can use it. So to calculate the levels, number of levels, so that is by what is the DC sources. So by using DC sources also you can calculate, that is 2n plus 1. We can take, like if there are 2 sources, so 2n plus 1 will give 5. So 5 levels output we can produce. So why I have highlighted here, now if we want to design a reduced switch type, now if we think of designing a reduced switch, here there are 8 switches are there. Now you see this circuit, what I have shown in the right hand side. What I am done here, Again, the same two DC sources I have used here, right? But what I have done here, I have used one switch S2. You just focus on S2. Why this S2 is used here? S2 is used to add these two sources, B1 and B2. Here, the motivation is that we need to add anyhow two sources to produce the higher levels in the output, right? So here, first switch S1, if I turn on S1, how this circuit will operate? If I turn on S1, then the current will flow through T1 and T2 in the positive cycle. So T1 and T2. So that will create a voltage step V1 first. Then in the second step, if I turn on S2, V2 and I will turn off S1. Obviously, if I turn on S2, I need to turn off S1. Otherwise, there is a short circuit here. So S2, if I turn on, V2, V1 will be added again. So that will create V1 plus V2 at the output. But the problem why I've connected S3, that is again an important aspect here. S3, if these two sources, if we consider they are unequal, if we consider these two sources are unequal, and like this is, let's suppose V1 is 5 volt, V2 is 10 volt, that is in the ratio of 1:2. Now you consider, or no doubt the 5 volt first voltage step will be created using V1, right? T1, T2 when they are operating and S1 is on. So in that case, first level will be obtained. Second level, if I want to create, that will be created only using this circuit, right? Say S3 switch. So why I have to highlight here why I've connected the switch in this way. And all the switches what I've shown here, that are and there is a anti-parallel diode across all these switches, right? So this S3 switch, if we turn on, and V2 is there, so in the S3 switch also there is an anti-parallel diode. Through that current can flow like this. So from V2 current can flow through T1, T2, and that can
Uh,
create a next step.
Kaibalya, maybe you
Yes.
can just pull up the paper if it saves you some time, because I think there you have described it very well, each phase. If
Yeah, yeah,
you,
yeah.
yeah, if you want,
Yeah.
otherwise,
No, actually, the focus here is switched capacitor type. So
okay,
I'm just going from how to design a switched capacitor, how the switched capacitor came
got
into
it, got
picture.
it.
Yes, sir.
Okay, okay.
So here, this switch S3, if I turn on, so that will be turned on when there is a loads here, inductive load. If we change the load from R to RL, because in power electronic, all these circuits in application perspective, if we think of, these circuits need to use with linear load or non-linear load, every different types of load, R load, RL load, and all this. So if we connect here an RL load, in that case, inductive load, because of the inductive load, reverse current need to flow. There should be a path for reverse current flow, right? So because of that, the S3 switch is connected in this fashion. So I will go to this inductive load current flow path in other slide. But here, the point to highlight here is that one switch, if I turn on S2, these two can be added, right? V1, V2 can be added, and that can create the voltage steps. So now you think the number of switches is now reduced to only 7 switches, right? So one switch has been reduced. So similarly, we can also think of reducing the switches and taking this module, the basic switched capacitor type in modules have been designed. So here if we see, I have just replaced, I told you, right, this S3 switch we do not need if we consider equal voltage sources. So considering equal voltage, like if I take only one voltage now, only one voltage source V, and there is another capacitor I have used in terms of the in place of V1. Now you again think of the same way. So first case, if I if I do not turn on any switch, first let us suppose in the first level, for the first level, what I do, I will turn on S1, the switch S1, and T1, T2 obviously because for the positive level output, T3, T4 for the negative level. So if I turn on T1, T2 and S1, what will happen? This current from the source can flow through capacitor C. Okay, so but that will charge the capacitor current obviously. So if we see here, current will flow in this way through the diode, through the capacitor, through the switch. So this way the capacitor is getting charged, and also current, because of the T1, T2 are on, current will also flow in this way, T1, T2 back to supply. So because of this, what is happening? This capacitor C is getting charged to the same voltage V, clear? And also at the same time, it is producing the first level. First level is produced here. So we have produced first level as well as the capacitor is getting charged. Then in the second step, what we do, we just turn on the switch S2 here. If we turn on switch S2, again what will happen? This supply voltage V and the capacitor voltage, current will flow in this way now. So the capacitor voltage, initially it has stored the charge, the same, it has charged to same voltage V. So now it will discharge. And again T1, T2 are on, let's suppose. So now the voltage across the output or the across the load will be this sum of the voltage source and the sum of the capacitor voltage, right? So because of that, there is a two step at the output. You see now, what is the advantage of this circuit? With this, what is the advantage we have got here? Different advantages. We have used single source, first thing. Second thing, we have not used any control circuit for the voltage balancing of this capacitor. That is getting charged in the positive half cycle in the first step. Then in the second step, it is getting discharged. And one more thing, one we have to focus here, that in one of the fundamental cycle, there is enough time for the capacitor to charge and discharge. So we do not need any voltage balancing circuit. In the first step, it is getting charged. Next step, it is getting discharged. So there is a self charging discharging process is there, that I can say in parallel it is getting charged, and in series when a turn on switch S2 is turned on, it is getting discharged. So because of this charge discharge in parallel and series, this topology is working. And how the output is produced here, you just see there are 5 levels at the output. That means there are 2 steps at the positive level, 2 steps at the negative level. And what is the advantage we have got in terms of photovoltaic system? If we see one source, we have got 2 times the output, because this is B, and the second step here will be 2B. So because of the addition of voltage across capacitor and voltage source. So because you are getting 2 times the voltage, so that is the advantage of switched capacitor type. We have, this is self-balancing switched capacitor modules, we can say. We have produced 2 times the voltage. Also we can avoid the DC-DC converters. Like DC-DC converter, if we think of in photovoltaic system, generally we are maintaining this 0.5 duty ratio to boost the voltage to 2 times. Now without using any DC-DC converter, we are boosting it to 2 times. So we have achieved the voltage boosting using single DC source. Also, another important thing is we have reduced the number of switches. If we see, with respect to the conventional circuit, this side what is shown, the 5 level CHV MLI, this is also producing 5 level. This is also producing 5 level. Here we are getting, we are using 8 number of switches, and here with using only 2 and 4, 6 switches, we can produce the same output, right? So that is that are different advantages of switched capacitor modules, I can say. So with this, there are many other switched capacitor modules that I have just summarized here in the different papers.
Kaibalya,
Yes, sir.
just one question. This capacitor can be any type. Is there any preference, or it can be ceramic, supercap, anything?
Yeah. Very good question. There, because of different applications, people have used different electrolytic capacitors can be used. I'm using that.
Okay.
And electrolytic capacitor. Main aspect of designing the switched capacitor inverter is the choosing of proper capacitance value. So
Okay.
that I'll also highlight in one of the
Okay.
paper. I have how I have calculated it.
Yes.
So these are different modules here,
Okay.
different modules, and this module I have just explained. If we see the in the previous slide, I've explained about this module.
Got it.
Okay,
Yeah.
sir.
Please go ahead. Yeah.
Sir. So here, this module, if you see, there are 2 switches, right? And 2 switches have different operation. When S1 is on, capacitor is getting charged. S2 is on, capacitor is getting discharged. So very simple operation. With this, I am achieving the 2 times voltage boosting here. So this is the basic module which is introduced initially in the switched capacitor multi-level inverter design field. And this is something similar. The second second module is very similar. There is no need of this switch actually, but some of the researchers, they have tried to avoid the number of diodes also. So that is why switch is used here. Then again, this is another module. If we see here, how to create steps at the output. You see, there are 2 capacitors, and 2 capacitors are getting charged in parallel with the DC source in this way. When it is charged, obviously these 2 will be charging in equal 0.5 voltage, right? So both the capacitors are charging to 0.5 B. So that is how we can again create number of steps at the output. Similarly, this is these 2 modules at the down. You can see These are most advanced modules, I can say. And because from one single source here, BDC, we can produce around 3 times the voltage, because there are two capacitors in both the circuits. There are two capacitors, and in first circuit there are in this module there are 5 number of switches, and in the this module there are 4 number of switches, and both the modules, all these modules whatever I've shown, that are all of self voltage balancing type. So we do not need any auxiliary voltage balancing controller. That is the advantage. So and utilizing only capacitors, avoiding this DC-DC converters and your transformer in the output side, you can boost the voltage. So that is the advantage. Only capacitors can be used to boost. And I have highlighted also series parallel voltage balancing. So what is the scheme is, in parallel it will charge and in series it will discharge. So by that fashion, if we maintain the switches turn on and off, we can definitely maintain the voltage across the capacitors. So you see that with this single source, we can able to achieve the voltage boosting using capacitive modules. So these modules again further can be used. I am not saying only the same modules can be used for designing any multi-level inverter. These are the different modules that authors or researchers have proposed recently. So this one I have highlighted here. Again, a important aspect. If we see here, this is another like inverter. The same module. This module what I've shown here just now. The same module, I can use it and I can cascade it again to create number of steps. I told this circuit, some of this and this will be producing 2 steps. Again, some of this and this will be producing another 2 steps. So there will be 9 levels at the output very clearly. So this is proposed by one of the researcher in this work I have highlighted here. Very early 2014, we can say it is proposed. And so what is the disadvantage point I want to highlight here is that, again, I am getting back to multiple DC source, what I have highlighted earlier. Because why we have gone to switched capacitor topologies, to reduce the number of switches as well as number of DC sources, right? Because we have to avoid multiple DC sources in terms of applications. That is different, based on different applications, different topologies are created, no doubt. But still, my focus is here exactly to reduce the number of source. So based on that, if we see, there are different sources here, which are different topologies that is highlighted here. You can see there are different advantages. Why these topologies are advantages are that these are using only single DC source. First, all these circuits what is shown here is using single DC source. This can be extended to create any number of voltage steps, right? You can go on extending. These dotted lines are there, you can see. So you can go on cascading these modules, so that can be extended to create higher number of voltage levels. When you go to higher number of voltage levels, obviously we have to evaluate whether we can reduce the switch or not. So I will not take too much time. I will directly go to my work now. What I have proposed here, you can see I have used a single DC source. This is one of the high gain type, M type I have named, because this structure something looks like M structure. So that's why I have named it as M type switched capacitor multi-level inverter topology. And this circuit, if we see, this requires single DC source. What are the features like single DC source is there? There are number of switches, that is 13 switches are used, and only 2 diodes are there. So here there are 3 capacitors. One capacitor is here, that is C1. Another capacitor is here, that is C2. So this module, this both C1, C2 are getting charged in the operation. They are getting charged to the same voltage as the input source. Whereas another capacitor here, that is C3, that capacitor is getting charged to 3 times. That is sum of this VDC input, this voltage across C1, voltage across C2. So all these 3 sources are combined, we can say, to charge this capacitor C3. So that is why this is getting charged to 3 times the input voltage. So what is the advantage of that? Advantage of that is that if I see only single voltage source, now if I add all these sources, what is there in this circuit, that is V here, and this 2 capacitor voltage, that is VDC, VDC again, so 3 times, and this capacitor is producing also 3 times the voltage. So total voltage will be 6 times the input voltage. So just think of in the DC-DC, in the photovoltaic system, we can avoid the DC-DC converters easily because we are achieving 6 times the voltage boosting, right? So based on that, again, I have shown here the circuit operation. I will just go through the first step. You see there I have shown here in the left hand side how this is creating the 6 steps in the positive and 6 steps in the negative. So that all operation is shown here. In the positive half cycle, if we see, if I make this switches turn on, whatever the red color path is there, the switches are turned on. So switch S1 is on, then it is going, the current is flowing in the red color path. So because of that, what is happening? In this first step, I am not charging any of the capacitors, right? But in the second step, in the 2 VDC level, I am just switching on the switch S5. So because of switch S5 is turned on, the current is also flowing in this way, the blue color path you can see. So that is charging the capacitor C2. So in this case, capacitor C2 is connected in parallel with the voltage source VDC. So because of that, capacitor C2 is charged to VDC. So like that, the C1 also can be charged to VDC and C2 can be charged to VDC. Whereas if we see the last step, 6 VDC step, which is the last step or the upper voltage level, you can see at that time capacitor C3 is getting discharged, right? All the capacitors are discharging in the path, so that is creating a 6 times VDC step. So that is adding this voltage source and the capacitor voltage are added together to produce the output. So this way charging and discharging is maintained in the one fundamental cycle, and also I am achieving the voltage boosting. So how to calculate? I told the main important aspect of designing a switched capacitor inverter is the calculation of the capacitors, right? So with to calculate the exact value of capacitors, what I've done, I have calculated it taking the longest discharging period. From how much, from what time to what time this capacitor is getting discharged. If we see here, I have highlighted here what is the longest discharging period of each capacitor, that I have shown here in the yellow line. So this is discharging from this period. So taking into account that period and the frequency and the output current, I have derived the formula from this basic principles. That is, charge stored in the capacitor can be calculated using this formula, right? And this row here, what I've taken, that is nothing but the ripple in percentage. So taking into account all these things, and this is the what is the, this is power factor angle, you can say. And that taking into account everything, we have calculated the capacitors. As I've told, this both the capacitors C1 C2 here are storing the same voltage, so that are taken equal and same charging discharging fashion also. But capacitor C3, which is storing the charge of 3 times the input voltage, that is calculated separately. So I have then to evaluate it, what I've done here, I have just taking different this percentage ripple value, 5%, 7%, 10%, 15%. Then we have calculated, we have got a plot here with respect to output voltage, the capacitance. So you see here, if we consider 5 to 7% of voltage ripple, so what should be the capacitance value? So 5 to 7% of voltage ripple means around this range of, we can say, we can take the capacitor value, right? So that is around 3000 or 4000 microfarad in that case. Again, similarly here, this C3 can be calculated accordingly, right? Considering 5 to 7% of voltage ripple. Similarly, I have again shown here different plots taking into account power factor. With respect to power factor, we have shown a plot here. So the main point is, here we have designed the capacitor based on the percentage voltage ripple we want to take into account, 5%, 7%, 10%, like that. So to evaluate the what is the superiority of this topology, I've compared with respect to different factors and different topologies that are there in the paper. These reference numbers, we can say from the paper, anyone can refer to the paper. So you can see here the number of switch, number of driver, number of diode, number of capacitor, what is the voltage boosting. Like some of the topologies they have considered 3 times, some of the topologies, here I have introduced the topology which is boosting the voltage to 6 times. Then the voltage, what I told, another important point is the this total standing voltage. So here I have taken total per unit standing voltage, or that is the voltage stress. into account. And also I've calculated a important factor, cost factor, that is given here in the formula. I've taken switch, driver, diode, capacitor, everything into account to calculate the cost factor. So if we see with respect to this cost factor is very, very minimum for the proposed topology here, right? So that is the advantage of designing this circuit. And number of switch also, if we see, that is also reduced. Here you see this topologies, why I am taking switch per level, driver per level, because different topologies, they have taken different level. You see this circuits, they are producing 7 level, and some of the circuits they are creating 9 level, and these circuits they are creating 13 level. So to give a fair comparison, I have taken different factors with respect to number of levels, and you can see it is still minimum, maintained minimum or optimum, you can say, to so that design is superior. That I have validated here. Again, there are some of the simulation results taking into account 30-volt source, only one single source, and as I've said, the output will be 6 times. So you can see it is almost around 6 times the input voltage, right? Around 180 volt, not exactly 180 volt, because there are ripples are there. So because of this voltage ripple, this peak voltage will not be exactly 180 volt, or RMS voltage will be reduced. But here one important point, you see this two capacitor voltages, that is your two capacitor voltages are equal, that is C1 C2, that voltages are maintained equal, and another capacitor voltage is 3 times the input voltage. So that is, this is maintained at nearly 330 volt, whereas this capacitor voltage C3, that is maintaining at nearly 90 volt. So similarly here I have another tested in another dynamic condition, when suddenly reducing the DC source voltage, that is automatically the voltage balancing is achieved, and the capacitors are getting balanced at a desired value. So that is the advantage of this circuit. And another point here, you can see when there is a change in the load, the grid, sorry, not the grid, the load current, because these all are tested in standalone kind of condition. And when there is a change in load, suddenly the grid, sorry, not the grid again, sorry, the load current is changing, whereas the output voltage, the voltage is still maintained the 6 times and stepped wave, which is not distorted. So that is the important point. So taking all these things, the experimental setup, what I've shown just earlier, that I have used for testing in different dynamic conditions with different loading conditions also. Another major thing in designing and this inverters is that controlling. I'm not going to highlight here the controlling aspects. Yeah, there are some of the papers earlier, I'll show you in the references, that I have used for evaluating the control schemes. So here I've used a selective harmonic elimination control scheme, that is generally based on how to eliminate the harmonics from the output voltage. So here you can see the inverter, when I'm changing the modulation index at this point, inverter output voltage is changing, but capacitor voltages are balanced, right? Again, the next case is I'm changing the load here. You see the resistive load when I've used initially, the output current, the pink one is the output current, that is also stepped wave and similar to the output voltage. Whereas when there is a suddenly change in the load, you can see the current is getting sinusoidal because of the low pass filter type characteristics. The current is getting sinusoidal. So when there is a sudden change in load, output voltage is not getting distorted, and also capacitor voltages are maintained as required, because the switching path is such that capacitor voltages will be always maintained, and I am producing the 6-time voltage boosting output without any auxiliary control scheme. Here you see this is about high switching frequency control scheme, and this prior circuits what I have explained, that is low switching modulation. So at high switching frequency modulation also, the output is still producing 13 level, and with change in modulation index, I told in earlier, as I explained, the levels will be reduced. So that I have tested here. Another test case results we can see here with non-linear load. Whenever there is a non-linear load in the circuit, how the circuit will, how the current will be. The current is non-sinusoidal because of the diode bridge rectifier type non-linear load. But whereas still output voltage is maintained, that shows the capacitor voltages will be definitely maintained. And another point here, with change in frequency, we can see that there is a clear change in the output voltage with change in frequency, it is still operating properly. It is producing 6 times voltage boosting, and all the desired things are maintained. Why it is tested in the change in frequency? Because I told in the starting itself, whenever there is a change or increase in the frequency, the capacitor voltage ripples will be reduced, right? So because of the reduction in ripple, this is one of the biggest application in high frequency AC applications. So this is the another results I can say, with different power quality analyzer results I've shown here. The efficiency I've got here is 94% approximately. And you can see, as I've evaluated the inverter topology operation using different control schemes, that is fundamental frequency control as well as high frequency control. So that total switching losses here I have calculated with respect to output power using different switching schemes. So as you can see here, at fundamental frequency control, the losses are reduced. Obviously, it will be reduced because the frequency of operation will be lesser at fundamental frequency, and at higher frequency, losses will be somewhat higher, right? So here with different output power also, we can see the efficiency plot. It is meant almost 94.5% at 150 to 200 watt output power. So, sir, can you just inform me whether I've
Yeah,
got much?
yeah. Maybe, yeah, maybe we can wrap up and take. There are lots of questions in the chat. Maybe we
Sure,
can
sure,
wrap,
sure.
yeah, and take questions
Yes, sir.
directly.
So, can I take
Uh,
another 2 minutes?
yes, 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 yes. Please go
Sure.
ahead.
Okay.
Yeah.
Thank you. Thank you. So here, after this, I have also proposed another inverter here. We can see. This is designed with the focus of reducing the voltage stress. You can see that you can just compare if we try to design a 13 level inverter using conventional system. So there the stress and everything number of switches will be very high, right? For 13 level system, for a conventional cascade H bridge, if we consider, the number of switches will be around 24 switches are required. But here the switches are reduced to only 12 switch. So using only 12 switch, again another inverter is proposed here. This inverter which boost the voltage to around 3 times here. You can see the voltage boosting is up to 3 times here maintained, but capacitor voltages, all the capacitor voltages are maintained as desired, and that is the advantage of these circuits. So this taking this circuit also, the positive cycle of operation I have shown here, and also I have highlighted how the capacitor is getting charged. You can refer the paper for more information how the capacitor can be charged in the positive and negative half cycles. And this is again a comparison conducted with respect to all the different terms, right? So with respect to all the different terms, you can say that superior. Here you can see the number of switches for 13 level. Here only for 13 level I have used this comparison, taken this comparison. Only 12 switches are used in the topology, whereas other topologies they require almost higher number of switches, right? Not only the switches, the other aspects like I've taken here important terms, the number of conducting switches that is also reduced, and number of switch facing stress more than the input voltage that is also reduced. So with respect to everything, there is a optimization of this circuit topology. So again, with the dynamic test condition, I'll go to some of the experimental results. Yes, here you can see with different loads, resistive load, RL load, dynamic change in modulation index, this output voltage is 3 times here because the input voltage I have taken 60 volt. So 3 times voltage output is produced, and all the 4 capacitors are maintained at the desired voltage. So no need of any auxiliary voltage balancing circuit, and also no need of any DC-DC converter in the photovoltaic systems. So I have highlighted here in the summary what are the different aspects to be considered for designing a efficient switched capacitor type or switched capacitor based multi-level inverter. That is no doubt reduction in the switches, DC sources, the stress, that is total standing voltage, and also peak inverse voltage. Peak inverse voltage is the individual switch, which switch is facing the maximum stress. That is another point. Then obviously voltage balancing, voltage boosting to be considered. Then I have shown the load handling ability like R load, RL load, nonlinear load. All these different loads has to be under different loading conditions, that topology needs to be evaluated obviously in the practical applications. So that is also one of the important aspects. Then losses efficiency. So considering all this, And one more major important thing, if we see in the recent design switched capacitor type topologies, that is the current. Because whenever we are suddenly charging and discharging the capacitors, there will be high inrush current. So with respect to high inrush current minimization also, this there is a good scope of work in the field of multi-level inverters. So with this, I'll end here. I thank the
Yeah. Very good presentation. Spectacular presentation, Kaibalya. Very good.
thank
Explained
you, sir.
very well. Lots of questions in the chat. We will take a few.
Sure, sir.
Kazim, can you please unmute yourself and go ahead? Kazim. Okay. Meanwhile, I'll just read out his
Yes,
question.
sir. Yes, sir, I'm
Please,
here.
please go ahead with your questions. Please go ahead.
Thank you so much. It was very great presentation. It was very helpful for me. Thank you so much. There are some
Welcome.
there are just some questions in order to make it much better understanding. Sorry, I have some question about the real maximum output voltage that we can achieve. We can achieve from this converter, because at higher power levels, output power levels, when the load current is high, these capacitors are discharged very quickly, and
Yeah, correct.
it I don't know, violate the appropriate high quality of the output voltage, and it leads to high THD. What
Yes.
is the practical, how much maximum output voltage can be achieved from this converter in real condition, in practical applications? And the other question is about the inrush current of capacitors. Two
Yeah.
capacitors are used for charging the third capacitor. This leads to a large voltage drift of these two first capacitors. And also, these are the main question. And the last question is the inrush current of capacitors. The inrush current, if you use I don't know, SIC or JN switches, this problem will be much severe.
Yeah, correct.
Kazim, let Kaibalya answer, then you can go follow.
Okay. Thank
No
you.
problem. Go ahead,
Okay,
Kaibalya.
thank you, Kazim, for your question. Very informative question you have asked. What I have not highlighted, I thought of highlighting at the end, like, regarding this inrush current, but not much time. So first thing, what you have asked about the voltage, what maximum voltage we can achieve, or how much maximum peak voltage we can maintain in high power applications. Definitely, this is the biggest problem of switched capacitor type topologies. What I have faced when designing this system, this high power or modules, the capacitor voltage ripples is too high, somewhat higher. So if capacitor voltage ripples, if we consider around 7 to 10%, in that case we cannot obviously achieve the exact output voltage of peak voltage like 6 times what I've shown in that inverter. We cannot achieve. So obviously the RMS voltage will be reduced, and that is due to the voltage ripples what I've told. So this capacitor voltage ripples is the major problem in these circuits. Now I will also want to highlight here, there are different topologies that are introduced now recently, that is focusing on how to reduce this charging time, discharging time, and that can eventually affect the reduction in the inrush current. So what is happening here, I'll just go to one of the case here. Yeah, yes, this one. Suddenly when one of the capacitor is getting charged or discharged, because of the charging to discharging state change, or when there is a sudden charging, so all this capacitor, one more thing I want to highlight here is that all these capacitors are pre-charged capacitors. So initially the problem of inrush current, sudden spike of current will not be there. But when the circuit is operating, at that time also it is getting charged and discharged continuously. So because of that, high inrush current is there. We have also faced the issue with high inrush current, and now the inrush current issues has been tackled by different authors by taking inductors, generally current limiting inductors they've used. So here in the second circuit, I can show you. Here I've used, yes, here what I've done here is I've used small inductors here to minimize the inrush current, or the inrush current to here. I've not included the result, but in the paper if we refer, the current has been reduced to around 4 to 5 times by using small inductors. So based on that, also different topologies are introduced to reduce the inverse
So,
current.
what is your opinion on power range? That is asking. What is the output power range that you suggest, or you feel it is appropriate for this
Power
topology?
range of, because I have personally, my personal experience, I have tested with 1 kilowatt design.
Okay.
Up to 1 kilowatt design I've already tested here, and it is working. But obviously
Yeah.
the size of
Yeah.
capacitor,
Your
because
focus was not on to scale the power. Your focus was on the topology, right? Just
yeah,
to
correct,
make.
correct,
Yeah.
correct,
Yeah.
yes, yeah.
Okay.
Not
So,
much focus I have given on this power scaling level and all,
okay.
but yes, sir,
Yeah. So
that is the
Kazim
basic.
has one more question. You also the two capacitors are being utilized to charge a third capacitor, which increases the
Yeah,
voltage ripple of the first two. This leads to low power quality and high THD.
correct, correct, that is correct. That is
Oh.
the problem here, because if I use two capacitors again added to charge another capacitor,
Hmm.
so that will again, because they create more ripples, and obviously THD also at the output will be increased.
Hmm.
But still the focus is to achieve here is to achieve high voltage boosting.
Hmm.
So to
Hmm.
boost the voltage, obviously using single DC source, we need to use
Hmm.
more number of capacitors. And using more number of capacitor will incur no doubt ripple losses, but still
Hmm. Hmm.
we can achieve voltage boosting. So that is the advantage I can say. If there is some advantage, some disadvantage also there. And
Hmm.
obviously main disadvantage is the inverse current aspect and the maintaining the peak voltage level
Okay.
at
Okay.
high power applications. Yes, correctly
Yeah.
he has pointed out, Kajin, and
Hmm.
thank you for that.
One
Yeah,
more question is maybe numerous devices are in the current flow path.
yeah, yeah.
So this leads to poor efficiency. Any comment on that?
Sure, sure. I have just highlighted one point related to that.
Hmm.
When I've compared this topology, if we see, I've taken another a term NSS.
Hmm.
Sorry, not NSS, NSC. So NSC term, this is the term. If we refer the paper, this term I have taken how many number of switches in the conducting path while creating the 13 level step. So here,
Hmm.
if we see the comparison with respect to all these topologies, you see there are only 6 switches in the conduction path, whereas the other, these all these papers, if we see, these are all recent papers. And all
Hmm.
papers, they've taken around 8, 7, 9, 12, 13 number of switches in the conducting path, whereas I have reduced to around 6 switches.
Got
So
it.
as
Got it.
conducting switches are reduced,
Hmm.
obviously I can expect low power loss and improvement in the efficiency. You can think of designing now novel topologies considering this aspect also. Yes,
Okay. Okay. So one last question he asks about cost function. How do you decide delta?
that is,
Kazim.
yes, correct, correct, correct point. I'll just highlight here. This delta and gamma, these are generally taken point one or less than one or more than one. So if we take equals to one, that means the number of switch and the stress that are given, both are given equal importance. If delta is taken zero point 0.5 here, as you can see here, zero point 0.5 I've taken. So if zero point 0.5 here, the stress is given less important. If it is more than 1.5, stress is given more importance than the switches. So likewise, this has been calculated the cost factor. I've taken 0 0.5, 1.5, you can also take 1. And these are the three different values generally we used to take to give importance to switch count, or to give importance to the stress, or they have to be given equal importance. So this is the
Okay.
weighted component we can say.
Okay. Kazim, any follow up or
Thank you so
all?
much. It was
Okay.
really brilliant structure. I have just one question to increase my information about switch
Sure,
capacitors.
sure.
Sorry, what's your selection between SiC or GaN-based switches? Which one you prefer? The normal switches with large on-state resistances, or the silicon-based or GaN-based switches? You know, in the GaN-based or SiC-based switches, you have low on-state resistances, which
Yes,
lead to a large inverse current of a capacitor, but lead to much better efficiency. But in
sure,
normal
sure.
switches, the inverse current problem becomes moderated, but you lose the efficiency. What's your selection? And at last, we all know that any converter has its own advantages and achieving these advantages is in cost of losing some others. Your structures are very brilliant. Thank you so much. Thank
Okay,
you
well,
for your nice presentation. Bye.
Yeah.
thank you
Okay,
so much,
one thing
Fazim.
I would like to add is, yeah, better to go with SIC, and
Yes,
because GAN is, and we should see what the focus of this paper was topology.
yeah.
So I think
But still,
other,
he has raised a very good question,
Mhm,
because based on this SIC and GAN devices, people are doing research on this inverter design.
mhm,
But my personally, I am sorry to say that I'm not experienced with this GAN devices till now. I've not used any of these devices,
mhm.
so I cannot personally comment exact information related to that.
Okay, no problem.
So
Yeah,
maybe we
we'll take
can look
one
at the
more,
papers.
some more
Yes.
quick questions. Banuchandra,
Sure.
can you please go ahead, unmute yourself and go ahead.
Good evening, sir.
Yeah.
Please
Good
go ahead.
evening.
Yeah.
Please go ahead.
So my question is, so first question is, so how to calculate the total standing voltage? So can you explain with one example?
Sure. Because I didn't get much time here, I have not calculated here. Let's suppose we consider one of the circuit. This circuit I am considering the switched capacitor type only, reduced switched capacitor type, and there are 6 switches, right? S1, S2, T1, T2, T3, T4. There are 6 switches here. So when this switch S1 is on, at that time switch S2 is off, right? Initially when switch S1 is on, T1, T2 are on the first level. So at that time this switch S1 is conducting, but at the second level, you just think when the switch S1 is off, S2 is on. At that time, how much stress this switch S1 is facing? So if we think of the switches when they are turned off, how much stress that is that the switch is facing, that here in this circuit, if we see S1, S2, both the switches are facing the equal voltage stress of V. Am I right?
Okay, sir. Okay.
Did you understood? S1,
Yes,
S2,
yes,
both
yes.
the switches are facing the voltage stress V when they are turned off, right? And here, because this at this point, at the blue point and the red point, what I marked here at this point, the maximum voltage is sum of these two V and capacitor voltage, that is twice the voltage, 2V, right? Because of the addition of capacitor voltage. So
Okay.
2V, the maximum 2V voltage is now appearing across T1, T2, T3, T4. So all these 4 switches, I can say they are facing 2V. S1, S2 are facing V and V. So total standing voltage, if we combine here, total standing voltage, so 2V times the 4 switches will be 8V, and this 2 will be 2V, right? So 10 times the input voltage will be the total standing voltage. I think I'm clear.
Okay.
Okay, but
So
you
one
had
more
one more
question, sir.
question. Yeah, please go ahead fast.
Sir, can you explain the procedure for selective harmonic elimination or nearest level count PWM technique?
So you have asked a good question, but I think I don't have much time now to explain about
Because you
that.
are utilized one, so
See,
low switching
see,
frequency
this
and
is
then high switching
Banuchandra,
frequency.
yes,
Yes, sir.
yeah,
Yes, sir.
maybe you can email.
Yes. Okay,
sure.
sir.
It will
Okay,
be
sir.
You
best.
can also refer to this first 2 papers. Here, my focus was only on harmonic elimination control scheme. I've used proposed 2 different control schemes or algorithms, you can say, for selective
Okay.
harmonic elimination. Or we can also contact through email for more information regarding
Yeah.
this.
Okay, sir. I will.
Kaibalya
Sure,
will be, yeah. Please put your question bullet points and send an email.
sure,
Certainly, Kaibalya will be able to help you.
sure.
We have one last from Himanshu. Go ahead, please. Fast. Last question. Okay.
Yes,
Yeah,
hi.
please go ahead.
Thank you for this nice presentation on multi-level converters.
Yeah,
My question is that when you are using, I will go back to the multi-source converter. When you are using, for example, say 2 sources, and
yeah,
you are connecting 2 solar panels,
yeah.
and you are using separate MPPT control for both of them.
Okay.
So, my question is, how is the voltage maintained at the desired level when the irradiance is changing?
Yeah, that is why we have used 2 different voltage controller loops. That is total voltage controller loop as well as individual voltage controller loop. So this kind of MPPT, what you have asked, that is actually called as distributed MPPT logic, right? So because of not much time, I have not highlighted also that part here. What is this distributed MPPT? Is we need to maintain the total decelling voltage, as well as we need to also maintain the individual decelling voltage with respect to change in irradiation, right? So because of that, individual MPPT is controller is used here, and the control logic is like clearly explained in the paper that I think I have highlighted in this presentation, and we can go through that paper to know more about the MPPT logic and control scheme.
Yeah, Himanshu, I would also suggest if you have, if you're, what is your background? If you just say, tell us so that Kaibalya also knows what is.
Yes, sir.
Yeah.
Sir, I'm a first year PhD student at IISc Bangalore.
Very good, very good.
Okay, very good.
Super.
Thank you. Thank you. Yes, yes, yes.
Yeah, please send a detailed email to Kaibalya. I'll be more than happy. And please go through
Yeah.
the paper also. It is incredibly well written, and most of the doubts will be cleared by the paper. But
Yeah.
I strongly suggest you email Kaibalya.
Sure.
He will be more than happy to direct you to some resources. I think, thank you very much, Kaibalya. Very spectacular presentation. Very good. And
thank you so much, sir. Actually, I should thank you for giving me this opportunity to present here my work. I also thank all the listeners for patience hearing.
Yeah. Very
Any
good.
doubts or any regarding yes, any doubts? I'll be available with my email ID. You can just refer to my papers in the Google Scholar profile also.
Yeah. Very good.
Thank you.
I had one last question. Did you isolate because I see you have your laptop? Was there any isolation between your control and power circuit?
Definitely. Without that isolation of the controller, I can show you here. Maybe the picture is not much clear, but I have other pictures also here. If we focus here, there are TLP 250 base isolator drivers are used here, and that driver circuits is actually for the two purpose TLP 250. It is isolating as well as amplifying the pulses. So that amplification, I have done it from this this supply. You can see the supply to driver here. That is giving around 12 volt pulse, and sorry, 12 volt supply to this driver circuit. So that's why I've used two like SMPS kind of things here for the supplying to driver. Yes.
Okay. One last question from Rajkumar. Please go ahead, Rajkumar. Please go ahead fast.
Good evening, sir.
Yeah, good evening.
How are you, sir?
Yeah, I'm fine.
No. Please go to the question fast.
Okay, sir. Sir, the basic question, sir. I think you mentioned a reliable word, sir. So, what is the reliable in terms of reducing switch point to multi-level inverter, sir?
Yeah, reliability and modularity I have mentioned in the starting itself. Reliability, modularity, in that term, I will what I have not highlighted, I'll tell you one more important point here. This circuits topology, what you can see on the screen, these are extendable, right? With using single switch, you see, we can say that this can be easily modularizable, or you can extend it to many number of levels, right?
Okay.
So this is one of the important aspects, and highlighting this aspect, I have a recent paper what we have published to extend the number of levels. So here this paper, the sixth paper, if you refer, that can be extended. So this cascade H-bridge type and all these multi-level inverters, they are proposed with the aim that so that we can increase the number of level, we can extend to higher number of levels. So that's how we can modularize, we can think of reliability evaluation of this multi-level inverters. And some discussion I think we have also made on this fifth number of paper about reliability aspect. So you can just refer it.
And one more question, sir. In the hardware, are used that nonlinear load? I mean, if the load will be is varied, that voltage source it will be stripped or anything voltage will be is going to change. Are you using
no. Load this diode bridge rectifier I have connected in parallel with the linear loads, and diode bridge rectifier, with that I have used a simple RL load, right? So that diode bridge rectifier is acting as a nonlinear load here.
Is it in the photo,
I think it is
direct switch rectifier with RL load, sir.
yeah, diode bridge rectifier with RL load, correct.
Okay, nice. What is the load L value, sir? What is the inductance for that?
That is, I think, 20 ohm. I've taken around 20 to very less ohm RL value.
Sorry,
And if
inductance,
you change, yeah, inductance, that inductance RL value, what I've connected to that diode bridge rectifier, that I'm telling, that is around 20 ohm, 20, sorry, millihenry, correct.
Okay. What is the core of that inductance? Inductor. Core?
Inductor. You are asking about diode bridge rectifier or the loads in inductor?
RL load, some inductor you're using as a load muscle, RL load.
Yeah. That is.
So he's asking about the inductance of that RL load. Is that what?
That is 20 million. I don't remember exactly. I think I have mentioned in the paper.
Rajkumar, do one thing. Rajkumar, please collect your thoughts and send an email. So that's obviously there are too many parameters to quickly show here. But good. Please email Kaibalya. I'll be more than first go through the paper. I think most of the parameters are given there, and then please email Kaibalya if you have any further questions. So thank you very much, Kaibalya. Hopefully we'll see more research work from you in the future. Very good explanation. We are grateful for your time. Thank you very much.
Yeah, thank you.
And thank you, everyone. And please contact Kaibalya. Please go to the papers and contact Kaibalya if you have any more questions. And we'll end the meeting. Thank you.
Yes. So thank you.